Exam. Here. The first thing to note is that this time I made it so that the statements are true. So you don't really need to worry about where the statement is wrong, which is easier to somehow refer back to what you have for the practice midterm. So for student t-test, it's a parametric test. This is something you should be aware of. So it assumes that your sample is Gaussian. Okay, so that's a basic assumption for t-test. So if you have a data that's distributed from something really different, then it will not really work well. For non-parametric tests that we are studying for this semester, we usually just assume that the distributions are the same for the two samples. So but yeah, that's pretty much it. Um, B part for the sequence x1 through xn all the way. And okay, so yeah, this is xn converges to x almost surely is the strongest. Um, converges in probability is the weaker one, and converges to in distribution is the weakest. Okay, so that's Mm, actually, this is a sort of like an exercise question for probability theory, okay, in graduate school. But here we just know it as a fact. So almost surely basically just means okay, the probability is one. But then you can see that the probability, the convergence probability just saying, okay, the probability here of the violation is gonna diminish to zero, which is much weaker. Okay? And then for convergence to distribution is even more. It's even weaker. It's just saying, okay, now your CDF is converging pointwise. Um, so C part, well, C part is basically putting down the statements in epsilon delta notation really clearly. Okay, so when it's bounded, okay, bounded in probability, just saying, okay, the we can for every epsilon we can find a bound and a starting index such that this probability here exceeding the bound is arbitrarily small. Okay, this is up to that epsilon that you choose at the beginning. And basically, you're starting from some index n all the way up. So it's not for all n, but you need that cap n there. And then when it's dominated by one in probability, you just say, okay, now this is now here you're not saying so it's not for any epsilon you can choose C and N. You're saying for any epsilon and C, okay, you'll be able to choose an N. So that's the difference. For any epsilon and any C, you can select an N. So remember that's basically saying for any epsilon well, it's essentially saying, okay, the probability of exceeding the bound for any bound, okay, for any constancy, for any bound, exceeding that bound will give you a diminishing sequence. So that's where we have this epsilon delta, and cap n. So that's just slightly modifying because remember originally we just say this converges to zero as n goes to infinity. Okay, so that part is now translated to epsilon and kappa. So that's just like calculus, the real analysis conversion. D part to perform a goodness of fit tests such as Kolmogorov Smirnov test and Anderson-Darling test. So the test statistic here is essentially not following a Gaussian distribution. So these two have specific limiting distributions, they are pretty different from normal. So especially for the KS statistic, that's a homework question, right? So, but I believe you guys need to look deeper into the distribution to compute the p-value. So that's something we're going to talk about very soon about homework too. Mm. E part is one example from lecture notes. So that's so which is also related to homework too. So yeah, right. Okay, so this one, well, this one is from the homework, and I think this is also in the practice exam. So, but mm, I think this one is pretty much pretty much not changed. Yeah, right, right. Okay, so basically, this is just applying the Markov inequality. What about the next one? I think the next one is pretty much similar also. Yeah, right. It's the same question. So for your exam, I would say you may think about revising your preparation strategy, especially for the final, because we do have a final. Okay, so we are trying to assign homework three, but it's maybe the end of this week or next week. So I'm not 100% sure, but we don't have a lot of homework assignments. Um, so the exams are going to be an essential part for the grade. Okay. Yeah, so that's basically we need to realize. So that's the exam. Okay, so this is we need to realize we have two random variables x and y. Okay, they are independent and identically distributed, and we have z equal to x minus y. So now you want to calculate the this is z equals to x minus y. So this is now we have two random variables. So you need to think about the joint distribution. Okay, so but fortunately the joint distribution can be separated because they are independent. Okay, so independence can split the uh, joint density function into individual density functions multiplied. So that's something you can integrate separately. Okay, and then remember when you talk about the event of z equal to zero, that means your x equal to y. So in terms of the xy plane, you only have a line. Okay, so you don't really have a region. You only have so this is x and y. Okay, so you're only lying on that line with slope one above. So in terms of the space, you don't really have area. So that's the problem. So you have you're integrating over this set. Okay, this area is zero. So now that's a measure of zero on the two-dimensional space. And then you're integrating on that kind of set that will give you a zero. So that's the problem there. So translating to dx dy, then you're going to see that, okay, y is free, but is stuck. Okay, x is stuck with lower bound of y, upper bound of y. So that's going to give you a zero. Okay, so this you're not really integrating uh, on a reasonable interval. Okay, so that's a zero there. So this is sort of like a validation of one of the results. So we're saying, okay, x and y, they are ID, and the difference should have a zero mean and a zero median. So here, this is giving the argument for the median, right? So x equal to y has a probability of zero. Okay, that means what? That means almost surely, okay, you will either have the difference of positive sign or negative sign. And here, then, when you calculate the sign of z negative, you're just looking at the region that x is less than y. X is less than y is what? Is this is x is y. Okay, x is less than y is actually the region that's in red, okay, is y larger than x. So that's so now if you're saying, okay, I let y to run free and I get the bounds for x, right? Then these are when y is free, okay, is running in the purple line. So from negative infinity all the way up to this point, which is x equals y. Okay. So that's the upper bound. This is exactly why we have negative infinity and y. And then you can integrate. Okay. So then the rest of the steps are just integrations. And here you just need a u substitution to get the 1/2 as the answer. Uh, Make sense? Okay. Okay, this is actually one of the questions from homework. Okay, so homework two. We have a dining service, and then we have the uh, wait time, and then we have two methods. Okay, we have method A that's giving us the reduction. So on different days and different staff, so it's basically sort of like independent observations. We have these numbers. And here we have a median test. Okay, so we want to see if the median is different from 5. So that's sort of like a really standard, um, kind of a simple hypothesis. Okay, so we're not really saying, so this is just one sample, okay, one sample, and we have you have a test statistic m sub a, which is the median. So essentially, you just say, okay, what about the median of my sample here? Is it 5 or not 5? So this differs from 5. Okay, so if in the homework or in the practice exam you have something less than another number, then you will need a one-sided one tail problem. Here we have two tails. And then basically saying, okay, I'll observe, okay, so you can choose to identify the samples that are uh, larger than your median, okay? Or you can try to identify the ones that are smaller. So here we have what? We have 5, so this one is smaller. Uh, that's it. So yeah, that's the only one. So basically, you're saying, oh, we see 9 that are larger than the median, which is much larger than 1/2 of the sample. Okay, so that tells you this is very extreme. So the one that's more extreme is actually t equal to 10. Okay, so you have t equal to 9, which is really extreme. Okay, and then you're gonna calculate p-value as the probability of how extreme that could be. So the extremeness, so this is basically away from 5, right? So 9 is extreme. Symmetrically, 1 is extreme, and then for 10 and 1, 1, 10, 0, they're also extreme. So you need you need to have 2 times the probability of the statistic being greater than equal to 9. And then this is a really simple computation that you can do because from the previous question, right? So the probability of less than mean and greater than mean is both 1/2. So this is just a binomial distribution in a sense. So and well, you can calculate by hand. Okay, so this number is actually 22 or 22 dividing 10 24. So that's the power 2 to the 10. Okay, so this is something you are able to handle by hand. So this is a number that's less than 5%. That tells you, okay, we need to reject. Okay. But then also it asks you to compute the rejection region. So what's the rejection region? The rejection region is basically you calculate the critical number. So now you know, okay, when t is 10, when t is 9, you reject. When t is 1, is similarly extreme, so you want to reject, right? But what about something else? So if t is a little bit less, let's say 8, what happens? So when t is 8, then you will have this one additional combinatorial number. You're just saying, okay, I'm choosing 8 out of 10 that are larger, okay, than the mean, excuse me, than the median. So, but unfortunately, this fraction here becomes roughly 1/10. Okay, that's much larger than 1/20. So, so that tells you what? It tells you when you have t equal to 8, then that's not an extreme to reject. Because that if that's the observation, then you don't really have the sufficient amount of evidence to reject. So the rejection region is indeed where the 0, 1, 9, 10, that's the range. So here, when we ask you to compute the rejection region, it tells you you are able to know almost everything about the distribution there, so that you will be able to compute the critical number to reject. Okay, and the conclusion is just pretty standard. All right, so yeah, well, if you look at the sign test, okay, the sign test is essentially really similar to what you have seen from just now, because a sign test essentially um, the probability of the sign being positive and being negative, they're both one halves, just like what we discussed earlier. So this is again binomial. Okay, so and the data size is 10. So indeed, the rejection range is the same thing. Okay, yeah. So, but of course, you still need to argue this as a fact. Okay. Uh, and of course, now if you look at the sign, right? So we use the first row minus the second row. We have all positives except for this one, right? So that's yeah. So there's only one negative. So this is the process is exactly the same as the previous question. Okay. So if you completely understand what's going on with the sign test or the median test, then you should be able to do really well in these two questions. Mm, all right. Number six. Okay, number six is a permutation test. So notice here, whenever we talk about a test that's a sign test, okay, or a permutation test, we just assume that null hypothesis is that the probability, well, the distributions are the same. Yeah. And the null the research hypothesis is that in fact they do not follow the same distribution. Okay. So that's the hypothesis. It's not really about a particular statistic. So that's something that I have a number of deductions for the homework. So, so what's the idea? The idea is that okay, we don't have a lot of samples for X and Y. Okay, so what we do here is if you assume X and Y follow the same distribution, then any permutation of the union of the data still follow the same distribution. But now notice that this statistic here is computed by the sum of squares. Okay, that's from the observation here. That's really extreme. Um, because here this is the sample average of x squared. Okay, so remember x here are plus minus 10. So the squares are just 100s, and we have a uniform of 100. So x squared bar is 100. Y squared bar here is we have plus minus ones, right? The average of the squares is 1. So the difference here is 99. So that's really extreme. Okay, so that's the only possible situation where you have this 99. Or the similar extremeness is that okay, now everything is now every large number here is in the set y, and then you would have negative 99. Okay, so so now this is again a combinatorial problem. Okay, but of course you need to think about this really carefully. Okay, so if you permute the union, then what could happen? So essentially, we have large numbers that are four of those. Okay, so four of those could be all in X, but there could be three of them in X, could be two of them in X, could be one of them in X, could be none of them in X. So there will be a few different scenarios for my permuted X bar, X squared bar. Okay, so the sample mean. So it's the formula here is 1/4 of 4 plus 99K. So the biggest possible is wait. Hmm. The biggest possible is where K is 4, so it's gonna be 400 over 4, which is 100. And the smallest possible is when K is 0, which is just 4 over 4, which is 1. So we see the extreme values right here. But then for K being not 0, not 4, then you have something fractional, right? Basically, once you have this underlying analysis, you would know that okay, indeed, these are very extreme observations. Okay, so and then you will be able to calculate the probability. So basically, when the test statistic is plus minus 99, you're gonna be similarly extreme. And then what's gonna be the probability here? It's gonna be okay. So this is arbitrarily choosing four out of the eight data. But then here we have two scenarios. They are basically just choosing four largest for the first set, and then none from the second. Okay, and then the other way around. That's two dividing by 70. Okay, so that's which is really extreme. So this is like a one 35th. Okay, so that's less than 5%. And of course, these steps here, they are just helping you with the calculation. Okay. So yeah, well, okay, so that's the permutation test. So permutation test is something that's not difficult to compute. Um, so it's likely to reappear in the final. So just as a comment. So many of the tests they have really intuitive methods. However, some of the limiting distributions are really complicated. So for the exams, I would try to make it less reliant on distributions. So in the final exam, I may give you the normal distributions to do some limiting because I try not to do that kind of question because it's a little bit more computationally expensive. However, the homework two, I do see common issues in the computation of p-values for those more complicated tests. So yeah, let's look at that. So yeah, so in the final, I may give you, but of course, you will see certain questions in the practice exam for the reference. So that's exam five. That's exam for our section five. Okay, so homework two. Yeah, right. Sign test. Okay. Sign test. That's actually one of the exam questions that we just covered. Okay. Yeah, sign rectangles. That's something we need to concentrate on. Hmm. Yeah, median test. This is this is exam. So exam, practice exam. Just make sure to refer to that for number one. So number four. I think this is the exam question. Okay. Here this is saying, okay, I have the method B and I'm looking at the less than proposed median, right? So that's yeah, exactly. make sure to study those questions because I think the common issue is that some of you guys actually forget to compute the rejection rate, which is by no means difficult, but just you just need to analyze and get a conclusion there. All right. What else? Oh, yeah. Okay. So let's talk about number two. So here, consider the context and the data of question one. Use a signed rank test and test whether there is a significant difference between the two data sets at alpha equal to zero point zero 0.05. So, um, so the sign rank test is basically we have the differences, and then we get the ranks for the values. And the way that we introduce, so to quickly look at our notes, okay, so mm, sign test. Yeah, sign rank test. Okay, so the test statistic. So I think, well, there are ways that you can play with it. Okay, some people would say the positive sign, the ranks from positive um, differences and the rank of the negative differences. However, here notice that if you put the things together, then the mean is on average is zero. Okay, so this is exactly why people would just utilize the variance of the whole thing. Okay, so the way that we do it is okay. I get the signs, right? I get the ranks by just ranking the absolute value, and then this notice that the things are independent. So here the variance of this kind of stuff is easy because essentially you remember you are just doing the sum of it's gonna be you have mean zero, okay? You have zero mean, and then the variance is gonna be what? The variance is gonna be just the second moment. So the sign times the rank squared. Now the sign is gone. It's just one, right? It's gonna be rank squared. And now notice that the ranks are what? It's just from one all the way through n. Okay, so in that sense, you just have like a sort of like a uniform thing. So in terms of the variance, it's exactly the sum of uh, k squared. Okay, so that's the sum of squares that you see. Okay, and then you can utilize the asymptotic normal. Okay, so you have W over the standard deviation. Okay, the square root of the variance. And then you utilize normal distribution to categorize. Okay. So then basically now p-value is going to be really systematic. So in terms of our problem, I would say, so I think, yeah, I don't think there's a lot of issues for computing the ranks and stuff. So let's go back. So homework. So just, so, so the differences. Okay. So we have nine positives and one negative. Okay, so we have nine positives and negative is one. And then the ranks are actually we have a two. We have a two. This is the rank of a two. It's a rank. Everywhere else, that's what? That's basically from 1 through 10, but not 2. Okay, so it's 1, 3, all the way to 10. So remember now, what's W? W is gonna be the sum I going from 1 through 10 of the sign of the difference multiplying by the rank. Okay. So now this is if you think about that plus minus, this is W plus minus W minus. So this is 1 plus all the way up to 10 minus 4 minus 2 times 2. So let me just write it this way. Because here you're trying to fill a 2 there, and then you compensate by subtracting another 2. So this is 55 minus 4, which is 51. So that's something you need to watch out for. Okay, and then for the variance, it's gonna be 10 times 10, 11 times 2n plus 1, which is 21 over 6. So, and then you will be able to utilize. So here you have to utilize the calculator in a sense. So this is 3 um, 85. Okay. And then what else? Then W over the square root of variance. Then it's approximately 2 point. If you round to 3 decimals, it's 2.599. Right? And then we match with the normal distribution. So here, p-value. Yeah, okay, so this, well, yeah, okay. So p-value equals to 2 times probability of this W over, so basically this value, so we are matching with normal, okay, so standard normal. So the standard normal random variable has an absolute value greater than or equal to this value, okay. Here, notice we have what? We have 51, so this is a positive number. So you're asking, okay, now the probability of the normal standard normal to be more positive than that or more negative than the negative of that. So essentially that's the probability there. And now we just go. So you can think about this as well. This is 2 times phi inverse of uh, negative 2.599. Okay, so because we're looking at the tails, so we look at the table, negative 2.99, 2.599. So normal table, negative 2.599. So 2.59, wait. If you want to round it to 2.6, that's totally fine, right? 2.59 is here, okay? 2.6 is here. So roughly speaking, they are pretty similar. It's 0.47 or 0.48%, okay? So this is 2 times 0.4, let's say 48%. So that's much less than 5%. So we can reject. Right. And then, so that's the p-value. And then what about the rejection region? So the rejection region, you need to think about, okay, so now this p, you're looking for p, 2 times p of the normal random variable to equating to some t, absolute value is now strict, exactly 5%. So basically, you're looking at what? You're looking at one tail that's 2.5%. So checking the table. Excuse me, that's not what we want. So look at 0.025, right? So 0.025 in the table is here. I'm going to highlight it here. Okay. So that's what? That's negative 1.96. Okay. So absolute value of t is 1.96. Okay. So that tells you what? It tells you rejection region is what? Rejection. Remember, what's the statistic? The statistic is this. It has zero mean, but it has a variance. It has a standard deviation. So we need to multiply this number here. Okay. So that will give you the bound. Um, so rejection region is negative infinity. So basically, the absolute value is larger than 1.96 times the standard deviation there. Wait, no, not that. You need to multiply by the square root of this. Okay, so you need to multiply by negative 1.96 times square root of 385. And then union that number to the infinity. Okay, so and here we have what we have 51, which is larger than that number there. 38. Okay, so this is negative 38.458. Okay, 38. So I think some of the submissions are using exact distributions. That's fine, and I think the numbers are really close to the numbers here. So although you have only 10 data points, but still these numbers are actually pretty accurate. Okay. So the true numbers are not significantly different from our approximations. What I'm talking about are these numbers. Okay, these numbers are essentially not really far away from the true. Then put it underline in green. Okay, so that's what we are expecting. So now the distribution is pretty solid. Okay, so that's just the standard normal. Okay, just the standard normal distribution. So make sure to know how to handle those. Okay. So that's the signed rank test. And the rank sum test is also so uh, highly related. So let me see. So the data are the same, but the treatment is different. So to quickly look at our notes, uh, rank sum. So what does it do? So we have two samples, X and Y, okay? So now they have the same cardinality. They're both 10 numbers. But then we take the union, okay? We take the union and then we get the ranks for the values. And then what do you do? So basically you have um, the ranks of X, okay? So that's my Q1 right here. And then the ranks of the other set, okay, which is going to be Q2. And basically, the statistic is this one. Okay, so it's going to be the rank sum. Okay, subtracting the rank if the numbers in X are the smallest. Okay, so you're subtracting uh sort of like the increment. Okay, from 1 through n to now your current rank sum, which is just Q1 minus sum of 1 through n. So now this one, what do we know? We know that the expectation, okay, the mean is n times m over 2, which is what? Which is like 50. Okay. And then the variance here is also not difficult to calculate. It's going to be 10 squared times 21 over 12. So now once all these are given, you can calculate. And now here this is also asymptotic normal. Okay. So now again, you can use the normal table to calculate. So here I'm not gonna be super so I think for the ranks, the majority of the class has done the submission and did the rank computation pretty clearly. But now once you have the normal, then that's pretty much it. So yeah, so you're looking at the normal distribution. Uh, the probability of the normal random variable being greater than or equal to that absolute value there. Okay, and then the rejection region is also similarly calculated. But just remember, once the critical number is the same thing from before, right? Because it's 2.5. We have two tails. So that's a critical number there for the fraction is 1.96. But then you need to do what? You need to multiply by the square root of the variance and then plus the mean, which is 50. Okay, so that will give you the range of ranks to rank sum. Okay, to reject. So because once again the statistics are here. Okay, so that's U1 and U2. So that's something you need to watch out for. So back to our problem. Let me erase that. So back to our problem. So this is let me put it down. This is number 2. And so number 3, where do I put number 3? So let me put number 3 here. Wait. Number 4 and 5. Okay, number 4 and 5 that are already covered. So number 3. So the ranks, I believe the majority of the submissions are fine. So U1 is Q1 minus, so this is the rank sum, minus 10 times 11 over 2, because that's n times n plus 1 over 2. Okay, the sum of the original rank if the things are really low. Okay, for my old data, for my data X. So that's going to be 63. And U2 here, U2 is sort of like calculated as a conversation. Is Q2 minus the same thing, which is 37. Okay, and the sum is actually going to be 100. Uh, So that's for sure. So the mean is 100 over 2. Yeah, right. So um, yeah, right. So remember, these are, if you add them up, that's going to be what? That's going to be the sum from 1 to 20. Okay. So that's the total rank for the union. And you are subtracting 1 through 10 and 1 through 10 for twice. So essentially, 1 through 10 are canceled. And then now 11 through 20, you're subtracting 1 through 10. So it's going to be 10 tenths, which is why here you have 63 and 37 add up to be 100. Okay, so that's the reason there, and that's also the reason why they are symmetric. Okay, so they are symmetric to each other. So the mean is actually just a 100 over 2, which is 50. So that tells you are able to calculate, and also the variance of U1 is going to be what? It's going to be 10 squared times 21 over 12. So this is 175. Okay. Or if you want to put it as 7 times 5 squared, that's totally fine. And now we are able to calculate the statistic for matching with the normal. So it's going to be this. So here, indeed, you need a calculator for this kind of calculation there. The difference is 13 over 5 square root 7. So this is approximately 0.9883. Okay, so this is not extreme as 1.96 from before. Remember, 1.96 from before is the rejection ratio, right? So this is not significantly large. So the p-value is going to be the 2 times the probability of normal random variable being greater than or equal to this value. And of course, we check the table, so you can round it to be 0.998. So, and of course, we look at the negative side because we're looking at the tail. So, wait, negative 0.98 is here. So pretty large, okay, 16.37%. So multiplying by 2, it's 32.7%. That's much larger than 5%. So that we cannot reject. Okay. So now for the rejection region. So once again, 5%. We have 5% equals to 2 times phi inverse of t. T here is negative 1.96. Okay. So the same thing from before. So that's reading from the table. So rejection region is, so just remember this is what this is, the expectation, which is 50 plus negative 1.96 times the square root of the variance. The square root of the variance, which is square root of 175. Okay. And then we union so this is now 50 plus 1.96. So remember they're not negation of each other anymore. Okay, but the only this part is opposite. Okay, and what's this number here? So this is roughly, you can think about the number here. This is roughly negative 2. Okay, so this is roughly 13. Okay, so it's roughly minus 26. Okay, so you roughly have like 24. And yeah, so the if you don't do that rounding, let me see. Yeah, 24 point, so 24.072. And this part is 73.928. Right. Okay. So this part is roughly negative 2 times 13. Okay. So this part is roughly 2 times 13. Oh no, this is a 5. 5. 26, 26, yeah, 76, yes. Yeah. So that tells you, what tells you, okay, we have the, basically you're saying, okay, if UI is less than uh 24 or greater than 76, then you can be confident to reject. So that's the rejection range here. Mm, uh, Make sense? Yeah. So basically, you're utilizing normal distribution, which is a fortunate thing for this kind of example. So for the signed rank test and for the rank sum tests, they will be able to utilize the asymptotic normal. Okay, and the approximation would not be too bad. Okay, that's number three. So number four and five, well, we have that in the practice exams. Okay, number six. So number six, we're saying, okay, the data may not be following exponential distribution. Um, so what do we know about number six? So what do we know about the exponential distribution? We have exponential where lambda equals one, and here the CDF. Let's just use it as a fact that this is cap f of x equal to 1 minus e to the negative lambda x, which is now lambda is 1, so this is 1 minus e to the negative x. Okay. So what does it look like? It looks like, so this is defined from 0 to infinity. Okay, so only when the input is non-negative. Because remember, for the CDF, on the left end is always 0. So we have what we have, um, 1 minus e to the negative x. So e to the negative x is decay, exponential decay. And now we have 1 minus that. So the asymptote is actually the horizontal. So yeah, let me sketch it quickly. So this one looks like this. Okay. There's a horizontal asymptote of y equal to 0. And now you have 1 minus this. Okay, so then this is 1 right here. Okay. So the function looks like this. Right. So and on the left hand side, it's gonna be horizontal. It's constantly 0 there. So that's our f. Okay, so this is f of x. So the CDF of the underlying distribution that we assume. Um, this is y equal to 1. This is x. Okay. Okay. So yeah, that's our distribution there. Now, what are the data? The data okay. So the mean here is 1. Okay, we assume that the mean here is 1. So basically, we want to see if the mean of the data here is also 1. So what we can try to do is we subtract by the mean and see what deviations are there. So we have what we have negative point, let me get rid of 0, negative 0.5, excuse me, negative 0.05, point 0.02, negative, okay, 0.02, and then point 0.05, 0.01, negative 0.01, and then 0.03, negative 0.03, and then 0 and 0. Okay, you can see pairwise they're canceling out. So yeah, that's that, right? And that's that, and these two, and these two. So indeed, the mean is 0. So it tells you what the mean. So indeed, data here has a mean of 1 and symmetric. So in the sense that the mean test will not help you at all because whatever mean test it should do, the sample mean minus the true mean is 0. So you will not be able to conclude anything from mean test. So we here utilize the Kolmogorov test. So what do we do? Let's quickly look back at our notes. So we are looking at the approximation using the empirical distribution function. Empirical distribution function here. Okay. Okay. So the where is it? Empirical distribution function is something like this. All right. So we just count how many uh, uh, data points are there that's less than or equal to my x value. So for any input x value, this is x0. So I'm gonna compute how many data are less than or equal to that value. So remember the numbers here, they are concentrated near one. So we actually will see really steep steps that are jumping up. Um, but yeah, every time for the counter, if you increase every time this is a singleton observation, then you're gonna add by 1/10, right? But that's actually not the case for some of the data here. So let's quickly and here let's be reminded that this this kind of behavior, okay, this kind of behavior is saying, okay, the standard normal, okay, is approximated by square root of n times the empirical density function, excuse me, the empirical distribution function minus the underlying distribution density function. So this is the square root of n right here. Okay, so this is very important. In terms of our statistic, where is it? It's here. Okay. So what do? We need to compute the supremum of the difference. So the biggest possible deviation from my CDF to the empirical CDF. And then once I have that, I multiply by the square root of n, which is square root of 10. That's our statistic. And we are matching it with what? We are matching it with this one. Okay. The Kolmogorov distribution is having a formula in the two equations in black. One of them is like this, but it's when x is less than or equal to 3.1, greater than or equal to 0, greater than 1. And the other one is this, okay, when x is less than 1, okay, be larger than or equal to 0.27. So, and of course, when x is too large or when x is too small, then you're just going to have zeros. Um, so that's the graph. Okay. Mm, so yeah, right. Then in the red book, okay, so in that book without a lot of theories, then they do have this kind of approximation. So basically, it's really up to what kind of k value, what kind of z value that you choose. Okay, so that's the statistic of our sample. So basically, excuse me, this is the limiting distribution. That's a random variable k, ks distribution, and that's our statistic. So we need to calculate the value, and then we compare with which number which range that we are looking at, okay? And then we're gonna utilize the distribution. So it's not easy by hand. So we do need to utilize the calculator in a sense. All right. So on the high level, let's look at the data. Okay. So they are really close to uh, to one, but what's the smallest? This is the smallest. Okay. 0.95. And the largest is 1.05. Okay. So now where are they? So if you think about the graph, so I'm gonna quickly highlight what the function looks like, and then I'll let you go. So this is one. Okay. So and here, what's this value? This value is actually on the CDF. Okay. So this is 1 minus e to the negative 1. Okay. So which is approximately, so yeah, let me write it a little bit to the left. Approximately how much? I do have a graph right here. So here, make sure to explicitly express f hat sub 10. Okay, so this is 9 pieces. Why? Because you have repetition. So you have repetitions. Okay, so 9 pieces. Okay, so this is a piecewise function. And that value is 0.632. And so when you are near point, so I'm making it closer. So this is my 0.95. And that's my 1.05. Okay. So what does it mean? It means originally at this point, there's a piece that's just at 0. Okay. On the left is just constantly 0. All right. And you have steps jumping every time it's increasing by like point one, point one, point one. And then, so you want to compare how when it gets to point 632. So the one smaller is 0.6, right? The one higher is 0.7. So it will actually go cross, and then you want to determine which number it is, and then eventually at 1.05 you are at the highest. So that this is my f hat of 10. Okay, so this is the empirical distribution function there. So of course, if you are looking at the deviation, okay, so that supremum is obtained either at this point or at this point, whichever one is larger. Okay, but then if you want to decide which one is a point, I think on the graph. Okay, so on the graph, this is 1.6. Okay, so at 1 we have 6 data points, and the next one is 1.01, which is 0.7. Okay, so all of a sudden it jumps higher than the curve. Okay, so this gap, okay, this is the supremum. So let me change it to, yeah, so this is the sup of f hat minus f. Okay, and this is how much? This is actually 1 minus e to the negative 0.95 minus 0. Okay, so that's this value, which is approximately 0.613. Okay, and the rest of the step is just multiply by square root 10 to this, and then match with the KS statistic. Okay, so here this TKS equals to approximately 1.9393. So there's a piece that we need to choose. So yeah, for the rest of the steps, I'm gonna copy below this page, so you guys can refer to to the further steps. But here it's not easy to calculate the rejection region, so we just calculate the probability. But indeed, it's going to be a rejection. So yeah, all right. So if you have a class, so that's the end of the class, right? Okay. So yeah, okay. So let me stop recording and.